But I don't know where. Yeah, my friend got it the skin. I got hardware to it. It will look white color. So it's like actually.
Okay, folks. Good afternoon. Okay, so we were halfway through the discussion of the sample questions. So in the last class we started from beginning to end to beginning. Now we follow the other order, beginning to end. I won't go all the way till end because we already covered half. So we will meet the attempt in the previous class in the middle. Yeah. Okay. So yeah, let's look at some of these questions. Most steps in synthesis and implementation of digital circuits involve a trade-off between speed and. Of course, there are a lot of trade-offs involved in the design of any system. Okay, whether it's hardware system or software system or whatever. And even in the design of hardware, there are a lot of different trade-offs involved. Right? We saw some of those, like power, cost, size, then ability to upgrade, and a lot of other issues. But the most fundamental trade-off in hardware design is between speed and cost or area. The amount of hardware required and the speed at which you can run it. Even pipelining, right? Pipelining increases performance at the expense of course, design complexity is there, but something more tangible is the amount of hardware required. Pipelining requires more hardware. Why would pipelining require more hardware? Yeah, in order to insert registers between pipeline stages, well, you need registers, right? And the number of registers that are required, or the number of bits that are required, is quite high, right? Like for example, if you look at execute register, the E register, there is a lot of stuff that is being stored in the E register. So if you look at the E register, the amount of data stored is quite big. So you see here in E register you have this, that's already 32 bits, another 32 bits, another 32 bits, then there is a 4-bit value here, and then there are all these bits. Some of them are single bits, some of them are 2 bits. So you can see it stores, I think over 100 different bits, and that's a lot of hardware, right? And is that it? This is a pipeline without any hazard resolution mechanism, right? If you need to add hazard hardware, if you add hazard hardware, the amount of hardware required increases even more, right? And then if you have stuff like branch prediction, which is absolutely essential for deeper pipelines, you need additional hardware. But all this hardware is thrown in with the hope that you are getting a better performance, better throughput. So pipelining in its most fundamental form is a trade-off between performance and area or cost or hardware requirement. Now, the 3 inputs needed, this I think was a quiz question, right? For synthesis are HDL code, technology library, and what is the third one required? Constraints. HDL code specifies the function and to some extent the structure of the hardware. Technology library specifies what are the building blocks that are available to us to implement the hardware. So the functionality that is specified by HDL code is realized using the various building blocks from technology library while respecting the constraints. And there are fundamentally two types of constraints: timing constraints and location constraints. Timing constraints specify what is the speed at which your circuit operates, what is the maximum possible delay between a point A and point B, etc. Constraints are very much technology dependent. You put in constraints based on what is the eventual hardware platform that you want to create or run it on. So if you go through the constraints file in your project, there is a .xtc file. Some of you might not have opened it. If that is the case, please do open it and have a look, okay, to see what is inside. One of the first things inside your constraints file is a create clock constraint. And you can see that the create clock constraint clearly specifies that we are targeting a clock which runs at a frequency of 100 MHz or time period of 10 nanoseconds. And that information is absolutely crucial for the hardware to optimize things appropriately. Because even for the exact same HDL code and the same technology library, you could have different configurations which could have different areas and performances. And generally, the two of them are conflicting, right? If you put in stringent requirements, like if you give aggressive timing constraints, the tool will try to meet it at the expense of extra hardware thrown in. So constraints. Constraints are optimization goals. It can also be physical or location constraints. Like for example, you might have inputs like A, B as inputs and Z as output. But eventually these A, B and Z should be mapped to some physical pins on the chip, right? And that mapping, that logical port to physical pin mapping is done through location constraints. Now question number 3, the number of registers inferred from the code below is? Yeah, 0. Because you can see there is no clock involved at all. It's a purely combinational circuit. There is no posage, negate clock or anything of that sort. All outputs are sum of product or product of some expression of all inputs. So here P, Q and Z are inputs and A, C, D, E, A, B, C, D, E are outputs. It's a purely combinational circuit. Now, critique the statement, a system using a ripple carry adder is slower than the one using a carry look ahead adder. Is it a statement that is categorically true? Not quite, right? We were just discussing that depending on the timing specifications, the synthesis tool or even the designer himself or herself might throw in more hardware to make it more performance oriented if the timing constraints are stringent. Like for example, if you want to do a 32-bit addition in 10 nanoseconds, you will pretty much have to use some kind of carry look ahead. If you try to do it with a pure ripple carry, rippling through 32 different stages within 10 nanoseconds can be quite challenging. Right? So it depends on the timing constraint. Now let's say your timing is a bit more relaxed. You will have the ability to use a ripple carry adder in that scenario. Like for example, if your timing constraint is something like say 100 nanoseconds, so your clock period can be up to 100 nanoseconds. So this doesn't sound like a stringent constraint. So it might very well be possible to use a ripple carry adder. So it depends on what your goal is. For a low performance circuit, you can afford to use a ripple carry adder, a low performance adder. Okay, it also depends on whether this adder is in the critical path or not. No point in trying to improve something which is not the bottleneck. Right? If there is some other circuit which is even worse than your adder, no point in trying to throw in money or extra hardware to make your order faster when it's not the bottleneck anyway. Right? So if your order is not in the critical path, don't bother trying to make it high performance, because you won't get anything out of it other than perhaps the satisfaction that your order is fast. It doesn't translate to an overall improvement in system performance. Now, draw the diagram of a hardware efficient circuit that is capable of performing a rotate right operation by any number of bits for a microprocessor with a word length of 8 bits. So how do you do rotate right? A hardware efficient way to do rotate right would be a 3-stage circuit where you do partial rotation in each stage, right? So you will have 3 stages, so something like this, 1 stage, the next stage, and the 3rd stage. It will be connected like this, and here it will be some variant of this. Yeah. And let's say the amount of rotation is SHAMT or SHAMT3, because it's going to be a 3-bit rotate. Because a meaningful number of bits of rotate is 0 to 7 for an 8-bit value, right? So this will be for rotation by an amount of 4. This will be for a rotation by 2 and a rotation by 1. That's the idea. So let's say SH in is the input. Okay, so you give the input directly to one of the inputs, and that input will be marked as input 0. Why? Because the first stage does not do rotation if the most significant bit, so here it is SHAMT3 bit number 2, and this will be SHAMT3 bit number 1, and this will be SHAMT3 bit number 0. So this is asserted only when you need to rotate by an amount 4. Okay, and if this is not asserted, you don't rotate. And when it is asserted, you will be passing a half rotated version, rotated by 4 bits version. So this will be SH in bit number 3 down to 0, concatenated with SH in bits 7 down to 4. So you are basically taking the 2 halves and interchanging. So if this is your 8-bit value, rotation by an amount 4 means this half becomes or comes here, this half goes here, right? So that's what we do. And now we know where we are getting, right? And let's say this is SH out A. SH out A will be passed as such if we don't rotate by an amount 2. So here it's rotation by 4, rotation by 2, rotation by 1. So if this middle order bit is 0, it means you don't rotate by an amount of 2. How about here? Here it will be rotation by an amount of 2. So here what you would have is, it's a right rotation. So what comes here is SH out, or what you need to give here is SH out A 1 down to 0. Okay, and SH out A 7 down to 2. So this is rotating right by 2 positions, so that your bit original bit number 7 now becomes bit number 5, right? And original bit number 2 becomes bit number 0, and original bit number 1 now becomes bit number 7, and original bit number 0 becomes bit number 6. That's the idea. Okay, so this, and same here. Here let me just label it as SH out B. So this is unshifted version, and this is SH out B. This is SH out B, so we just have a rearranged version here. 0 here, SH out B, bits 7 down to 1. so that your least significant bit now becomes the most significant bit, and every other bit is shifted right by one position. Okay, so that's it, and that gives you a rotate right circuitry. If it was shift right, this would have been filled up with, it wouldn't be this if it is just shift right rather than rotate right. So what would these be? Zeros if it is logical shift right. It will just be MS base duplicated if it is arithmetic shift right. Okay, so that completes that. Now, in the addition of two unsigned numbers, V and N flags are never set, whereas C and Z flags are set based on the result of addition. Is it true or false? V and N flags are never set. C and Z flags are set based on the result of addition. V and N are indeed relevant only for signed numbers. So for unsigned numbers, V and N are not relevant. But that doesn't mean the hardware doesn't set it. Simply because the hardware doesn't know whether you are dealing with signed or unsigned numbers. The circuitry that is used for addition is exactly the same irrespective of whether you are dealing with signed or unsigned numbers. So the hardware doesn't know, the hardware doesn't care. Right? So the hardware will simply do the addition numerically and will change N, V, C and Z accordingly. And you could argue that the hardware is actually making an implicit assumption that it is dealing with signed numbers when it deals with V and N flags, and unsigned numbers when it deals with C flag, and zero flag is applicable equally for both. But that is just a way to look at it. In reality, the hardware doesn't really care. Okay, hardware will modify N, Z, C as well as V as appropriate, and it is up to you as a programmer to decide which bits you are going to check based on your understanding of what is the number system that you are using. So for example, if you use, let's say, R1, R2, R3, where you know R2 and R3 contains unsigned numbers. You as a programmer know that R1, R2 and R3 contains unsigned numbers. And the next line you are using is VGT. You are doing it horribly wrong. Why? Because GT is a condition that is to be used for signed numbers, not for unsigned numbers. And if you look at the expression for GT, or the combination of flags evaluated, you will see that it uses V flag, N flag and zero flag, not carry flag. And V and N are supposed to be checked only for signed numbers, whereas our assumption was that R2 and R3 contains unsigned. So you are doing it wrong. Will the assembler complain? No, it doesn't, because it doesn't know whether you are dealing with signed or unsigned. Assembler does not do any kind of type checking, any kind of adjustment for you. Okay, C compiler does, but in a rather weak fashion, but it does. But assembler absolutely doesn't. It doesn't give you any kind of error or even warning. So you will be doing it horribly wrong. Your results will be different from what you expect, especially in some circumstances. It actually might not really show up if you are dealing with relatively small numbers. Okay, many of these issues manifest when you are dealing with bigger numbers. Okay, and so that's the importance of making sure that you test your system or program or whatever with appropriate number of test cases, including those edge and extreme cases. Don't choose test cases that are convenient for you. Okay, choose inconvenient cases. That's when you will be able to realize if there are issues. Now, the number of NOT gates required to convert a 64-bit adder to a 64-bit subtractor is 64. Because you have to flip every single bit. A minus B is A plus B bar plus 1. And this B bar or complement of B is 1's complement of B. 1's complement of B requires every single bit in B to be flipped. Yep. In fact, I had mentioned that during the class, right? That, just because there is only one NOT gate drawn in the diagram does not mean you require only one NOT gate. It is a bus. So I had drawn something like this, but this is like this. So this means that there are 64 NOT gates, not one NOT gate. Okay, now memory systems. An associative cache is usually used for TLB. TLB is translation look aside buffer. What is that? In systems that use virtual memory, the address issued by an application program is in the virtual space. It is converted to a real physical address which is required for memory access, which is required to access RAM through an address translation process. And for that address translation, you require a table which is called page table. And typically the page table is big because real world programs use a lot of memory, so a lot of pages, so the page table could be quite big. So it cannot be contained in a cache or an easily accessible form generally. So it is typically a part of your main memory itself. So every memory access typically will require, or every memory access will theoretically require two accesses. One to read the page table to get the physical address, and the second one is the access using the real physical address. But two separate memory accesses for every memory, to fetch every word from the memory can be quite inefficient. That's why some frequently used part of the page table itself is stored in a special cache called translation with a side buffer. TLBs are usually very, very small. Even for the most modern processors, TLBs are extremely small because the chances of a hit in the TLB is typically very high. Okay, a program does not really typically access memory in a very wild manner, so TLB hit is a very likely scenario. So that's why it is quite affordable to keep TLB low. And since TLB is pretty small, many computers use fully associative cache for TLBs. Now the question says that it uses associative cache because the circuitry runs faster than other circuitries. That is of course not true. What is the reason why TLB is typically implemented using fully associative cache? For very small memories, the amount of search that you have to do is not so much. In associative mapping, a block from main memory can go to any block within the cache. And you have to, whenever an address is issued by the processor, you have to match the tag of the address with the tag of every block in the cache. And this is a very time consuming process for large memories or large caches. Whereas for small caches, like if the cache can hold only like 8 or 16 entries, then that search is possibly quite okay or affordable to be done for every memory access, right? Even though the circuitry is still not so simple, because 8 or 16 comparisons will require fairly complicated circuitry, but the time taken is not so bad. Whereas if your associative cache is much bigger, then the time taken to do a tag matching, that is to check whether the required information is present in the cache or not, can be very high. Okay, so but for small memories it's quite affordable, so it's okay to make small memories fully associative. And there is an advantage too in making something fully associative. What is the advantage? Any main memory block or a main memory block can go to any block within the cache. You have full flexibility. And full flexibility usually means efficient utilization of the cache. Right? You wouldn't end up in a scenario like you are renting a room in Marina Bay Sands and letting it lie vacant. You wouldn't do that, right? So same thing here. So if it is a small enough memory, it is beneficial and it is ideal to make it associative so that whatever memory is available to you, the number of blocks available to you can be optimally utilized. If you have too many restrictions regarding using an already small cache, your performance will likely suffer. That's the idea. Now, so the answer is false. The first part of it is sort of true though. An associative cache is typically used for TLB, but the reason is not because it's faster. In fact, associative cache is not fast, but the reason is because you want to have high hit rates, and the circuitry is not outrageously complicated. The time taken is not too high because the cache is small. Now, a write-back strategy will be more appropriate for a system executing programs where most of the data is stored in arrays. It's true. What is write-back? What is a write-back strategy? When you have a cache, let's say this is your processor, this is your cache, and this is your main memory. So a portion of the main memory, let's say this block, is brought into the cache as a cache block. So what happens when the processor updates a block within the cache? One option is to reflect that update directly into the main memory, as and when the processor writes. So every write is reflected back to the main memory. But that can result in a lot of unnecessary writes, okay, which can cause a lot of time overhead. So what many real world memories or caches do is to update only the cache and mark the cache as dirty. So eventually when the cache is flushed, that is, it is kicked out, the cache block is flushed, the cache block is kicked out by a replacement algorithm to make way for something which is deemed to be more urgent. The entire content will have to be returned back to the main memory. So the idea is you update within the cache, mark the entire block as dirty. So when the block is kicked out of the cache, you write the entire block back to the main memory. And this is advantageous in scenarios where there are a number of locations in the same block that are updated, or one location is updated over and over and over. Then you can keep updating within the cache itself and write it back to the main memory only after the entire block is processed, sort of. So indeed, write-back strategy is preferred in such a scenario. Now, in an associative cache, the worst case number of comparisons required to check if a word of interest is present in the cache, given that the CPU issues an m-bit address and the cache has 2 raised to n blocks, is, what is the answer? The CPU issues an n-bit address. So your main memory size is 2 raised to n. Your cache is fully associative, and the number of blocks within the cache is 2 raised to n. What is the number of comparisons required? It's 2 raised to n. Okay, m is irrelevant there. Why is it so? We saw in a fully associative cache, a main memory block can go to anywhere in the cache. So when an address is issued by the processor, the higher order bits of the address, which will be interpreted by the cache controller as tag bits, have to be matched against the tag of all the blocks that are present in the cache. Okay, if you are lucky enough, you could get a hit before you do the complete comparison, but in the worst case, you may have to do a comparison of the higher order bits of the address issued by the processor with the tag field of all the blocks from the cache, because a main memory block can go to anywhere in the cache, right? So that's why 2 raised to n possible comparisons. In general, the number of comparisons that you need to do is equal to the degree of associativity. And in a fully associative cache, the degree of associativity is the size or the number of blocks in the cache. Whereas in a set associative, the number of comparisons you have to do is the number of blocks within the set, because there is associativity within the set. Now next, a memory system using smaller block sizes is very likely to have a lot of which kind of misses? Compulsory misses. What is compulsory? What is a compulsory miss? A miss that is encountered when a particular word is requested for the first time, or a particular block is requested for the first time. Now, if you have a larger block size, it means one block itself contains more data. So, the first time you access a word within the block, you will have a miss. But you don't bring in just that word, you bring in a complete block into the cache. So the next time the probability of finding a word within that block is higher if the block size is higher, right? So the probability of compulsory misses is lower. That's the idea. Now, which of the below properties is LRU replacement algorithm based on? LRU is least recently used. It's a replacement algorithm whereby something which was not used in the recent past is a good candidate to be replaced or kicked out. It is based on temporal locality of references. It's based on the principle that something which was required recently is likely to be required in the near future as well. So that's temporal locality of references. Okay, which happens all the time in real world programs. Like for example, you have a for loop, for I is equal to something something. Then let's say A of I is equal to B of I plus C. So if C is required in this particular iteration, it's very likely to be required, or in this case it is certain to be required in the next iteration as well, right? So something which was accessed recently is very likely to be accessed in the near future again. So that's temporal locality of references. So it's a good idea to keep that particular block in the cache for as long as you can, as long as it remains accessed recently. Now, for a negative offset in LDR-STR instructions, sign extension of the immediate is necessary to obtain the correct result. Do you have to do a sign extension of the result? Sorry, like a sign extension of the immediate? Remember your memory instruction format? In memory instruction format, you had, of course, the first 4 bits are the condition bits, then OP is 0, 1, then you had your func field, of which one of the bits is U bit. If U is equal to 1, it means the immediate is to be added to the base register. Then you have your base register Rn, then the source or destination depending on load or store Rd, etc., and then finally you have your immediate. So this immediate is added to Rn to find the effective address if U is 1. It is to be subtracted if U is 0. So do you need sign extension of the immediate? The answer is no. You can think of it as a sign and magnitude system where the magnitude is encoded as the immediate and sign is encoded as the U bit. You will never do a sign extension to something which is a magnitude. Magnitude means it's always positive, right? So you wouldn't do sign extension. What if your most significant bit is 1? Extending it by putting more ones in front will change its meaning, because the number is not signed. So this part is purely magnitude. The magnitude itself is unsigned. The concept of sign comes in only through U bit. So immediate itself is unsigned. So you wouldn't do sign extension. Sign extension is done only when you are looking at a branch instruction where the immediate is explicitly mentioned to be signed. It's a negative number if it is a backward branch. If it is a forward branch, it's a positive number. So you are doing PC plus 4 plus that offset, and that offset itself is signed. So only for branch instructions you do sign extension. For memory as well as DP instructions, you will do only 0 extensions. You can see it here. Here, you see, it's a 0 extension for DP as well as memory. Only for branch you do sign extension. Because immediate for a branch can be positive or negative, it's a signed quantity. For the other two, the immediate itself is unsigned. But for memory instructions, there is a notion of sign that comes in through U bit. So it's entirely possible to write something like, say, LDR, R1, R2, minus 4. This is entirely legal, where 4 will be encoded as the immediate, and this will cause U bit to be 0. Okay, so it's sort of a sign and magnitude system where the sign comes from U. So this is sort of sign and magnitude. This is signed, and this actually is unsigned. An instruction such as add R1, R2 minus 4 is, strictly speaking, illegal. It is legalized only by the assembler substituting it with a sub instruction. So the assembler will substitute it with sub R1, R2, 4, and that's how it is legalized. Okay, you cannot encode minus 4 as an immediate, because there is absolutely no way to accommodate that sign. Okay, but having said that, one food for thought for you. It is possible and it is legal to have certain negative numbers here, and the assembler will still retain odd. Think of that possibility. Okay, hint, that can be done only with some rotations. Okay, your normal 8-bit unrotated value will be always positive. Okay, next, it's not possible to include support for DP instructions with register shifted register SRC2 in the single cycle processor described in chapter 3 without modifying the design of the register file. Is it true? Yes, it is true. Why? For register shifted register, how many registers do you have to read? For example, if the instruction is something like, say, add R1, R2, R3, LSL 4, LSL R5. So here your second operand is R4, R3 shifted left by an amount specified in R5. How many registers do you have to read in total? 3. This, and this. This is specified as RS. This is RM, and this is RN. So you have to read 3 registers in one shot. And for a single cycle processor, all 3 will have to be run in the same cycle. Right? Because the whole instruction has to be executed in a single cycle, right? And your register file, based on your chapter 3 design, can only read 2 values. So if you read a third value, you have to modify the register file. But later on, with the wisdom that we attained in later chapters, we know that it is possible to keep the register file design as such and still have this instruction. But it won't be single cycle. How do you do that? It can't be single cycle unless you change the register file design. But if you want to retain the register file design, don't want to change it, you have to compromise on the number of cycles. But assuming that you are allowed to compromise on the number of cycles, what will you do? You don't want to touch the register file, but you want your processor to be able to do this. Yeah, micro operations. Basically split this instruction into two. And the instructions to which it is split into need not even be instructions in the valid instruction set. Then freeze your PC for one cycle. Because now one instruction is executed as two, right? So you have to freeze your PC for one cycle so that another instruction will not come in. And then send these two over two different cycles. That's the idea. So how do you do it in this case? How do you deal with it in this case? What are the two possible instructions you can split into? Well, these two instructions need not be valid instructions like I mentioned earlier, but it's entirely possible to split it into something like, say, move, R3, some R temp. So R temp, which is not visible to the programmer because this is purely an internal detail of the processor. So move R temp, R3, LSL, R5. Now technically you can implement it using the same register file. Of course you have to modify your design a bit because now you are reading only two registers. This is your destination register. Okay, and then the next instruction after this can be R1, R2, R10. R10 is not visible to the programmer. So internally you will require more than 4 bits to encode these instructions now or registers now because you have more than 16 registers. Just that it is not visible to the programmer. But internally you have more registers. That would mean that you will require more number of bits to identify the register. Okay, there is sort of an internal renaming, but not exactly. I mean, not the conventional register renaming to improve performance. Okay, so that's the idea. So once again, this is not a register that is in the visible instruction set or visible register set. Okay, and with register renaming, we sort of saw that these registers need not always correspond to real physical registers. These are just abstractions that are used by the software to convey information regarding what is to be done to the hardware, rather than something which has to have a real physical counterpart. Yeah. So registers are just an abstraction rather than something physical. That's a story that we learned through register renaming. So here, in some sense, it's an internal renaming that is done. Okay, not to improve performance, but for being able to execute these two as two separate instructions over 2 cycles, which allows us to retain the register file design as such. Yeah. Now, next question. TEQ has the format TEQ RM RN and works in a manner similar to EORS, except for not updating any register except any such CV flags. An engineer who is implementing an ARM processor found that the implementation of EORS is working perfectly, but TEQ has a bug. Okay, even though RN and RN are found to be unchanged by TEQ. The ALU as well as ALU decoder was verified to be working properly. Write a test snippet code which will produce an erroneous result if TEQ is incorrectly implemented. Okay, this is something I had hinted about at that point when I was talking about single cycle processor design. But I realized that some of you still made that mistake for lab 1. Okay, the exact same mistake was there for lab 1 for some of you. Now, what exactly is the problem here? The story is that, well, TEQ is supposed to be performing in a manner very, very similar to EORS. So EORS, R1, let's say R2, R3, is supposed to do R2 XOR R3 and store it in R1. How about TEQ? TEQ is quite similar except that it doesn't have a destination register. So destination register is not modified, but it will set the flags the exact same way EORS sets flags. Just that no destination register is modified. So no destination register means it doesn't have RD field. So RD field, if you look into the ARM instruction manual, is mentioned to be SB set. Should be zeros. Okay, so the encoding for EORS and TEQ is quite similar, except for two things. One thing is that for EORS, the RD field, which is bits 15 down to 12, is 1, 0, 0, 0, 1. Whereas for TEQ, the 15 down bits 15 down to 12 will be 0, 0, 0, 0. But that alone does not guarantee that it will not be returned. And that is where the problem lies. Just because RD is 0 does not mean it will not get returned. For a register to not get returned, reg write should be 0. Okay, which apparently doesn't happen here. And what is the implication if reg write is not correct? If there are issues with reg write implementation, for reg write for TEQ should be 0, whereas for EORS, reg write should be 1. Because EORS commits the result to a register, TEQ doesn't. Okay, doesn't change a general purpose register other than flags. So if reg write is 1 for TEQ because the implementation was incorrect, it's not R2 or R3 that gets modified. It is R0 that gets modified. Even though R0 does not appear anywhere in the equation or anywhere in this whole story, you will end up modifying R0 accidentally if reg write is not 0 for TEQ. And some of you had already experienced that. Some of you came to realize that there was a mistake later on. Some of you probably did not even realize because you did not use R0 after that. Okay, if there is any instruction that makes use of R0 after this TEQ, you will see that the value of R0 has now been erroneously modified, inadvertently modified. Yep. A lot of you just looked at the value of R2 to see whether it was modified. R2 wouldn't have been modified anyway. R2 is actually a source, nowhere close to being a destination. Right? So, a program that makes use of R0 after TEQ, any program, will run erroneously. That's the idea. Okay, so as long as there is an instruction which makes use of R0 after TEQ, it's already a good test program. Of course, the instruction should do something meaningful, and then you will see that the result is not what you expect. So basically, no write implementation for some of you were wrong actually, or no write was not connected to 0-volt reg write. So if you go to this chapter, no write is a signal that should be asserted for instructions which do not modify registers. So no write should be 1 for TST, TEQ, CMN and CMP. So when no write is 1, reg write is 0. Okay, so some of you either did not generate no write correctly or did not connect it to this AND gate equivalent or AND gate. Yeah, so that's a mistake. Now, a 5-stage pipeline processor without any hazard detection circuitry can still operate correctly if the compiler has precise knowledge of microarchitecture and generates code appropriately and would still have a better performance than the corresponding single cycle processor. Is the statement entirely true, entirely false, mostly false, entirely false? Well, in practice, this statement is true. Why so? In real life, it's true. You see, the clock period of your single cycle processor is 900. Your clock period for your pipeline processor is 300. Which means your pipeline processor runs 3 times faster. Right? Your clock frequency is 3x. So, if 1 out of every 3 instructions in the pipeline processor is useful, then the 2 of them will have the exact same performance. Because you see, for a single cycle processor, 1 instruction completes every 900 picoseconds. For a pipeline processor, 1 instruction completes every 300 picoseconds. So 3 instructions complete for every 1 instruction of your single cycle processor. If 1 out of these 3 instructions is useful, the 2 of them will have the same performance. What are the chances of 1 out of 3 instructions being useful? Very, very high. It's almost always the case, right? So let's say you have, R1, R2, R3, NOP, and then the next instruction can make use of R1 now, because in the case where pipeline registers and register file are written in different packages, the spacing that we need is 2 instructions, right? So the next instruction can be something which makes use of R1, no issues. And if every instruction is like this, like for example, every instruction is dependent on the previous instruction, then you will have the exact same performance for both. But this is already stretching it quite a bit, right? Like every instruction being dependent on the previous instruction is a really, really worst case scenario. But now we haven't considered control hazards. For control hazards, depending on the stage, you will have to have a certain number of NOPs after that. For example, if you are taking your branch in execute stage, you need to have 2 NOPs per branch. And here again, you are looking at 1 out of 3 being useful. So only in an absolute worst case scenario, your performance will actually tally. But in practical scenarios, you will have more than 1 out of 3 instructions that are useful. So in practice, you will be able to get a better performance in spite of having to put in a lot of NOPs. But you can always come up with a theoretical example of a program where there is no performance improvement. Okay, so I can only say it is mostly true, because if you want to play nasty, it's possible to write a program where this is not true. Now, if the hardware is capable of doing dynamic branch prediction, an incorrect prediction will cause a reduction in dash but not dash. What reduces and what doesn't reduce? If you make an incorrect prediction, what is the price that you have to pay? You will end up wasting a few cycles. So you will end up wasting or reducing performance. But what doesn't reduce? Correctness the program correctness. Because anytime you make a prediction, anytime you have a system that makes a prediction, the system designer has an obligation to make sure that there are mechanisms whereby an incorrect prediction will not cause incorrect program execution. Okay, this can be done as a combination or through a combination of hardware and software, or purely in hardware. Okay, but either through hardware-software combination or purely by hardware, you have to have mechanisms which check for correctness of your prediction and mechanisms to ensure that incorrectly executed instructions do not change the program state, and mechanisms to flush those instructions and start the pipeline at the correct location or with the correct instructions. Now next one, we can increase the clock frequency by increasing the depth of pipelining. That is correct. You can keep on increasing clock frequency arbitrarily, but after some point you will realize that any attempt to increase the clock frequency has diminishing returns. Okay, you throw in a lot more hardware only to get a very small improvement in clock frequency. Deep pipelines can increase IPC beyond 1 even with a single issue. IPC is instructions per clock. With a single issue processor, the best IPC you can hope for is 1. You will not be able to execute more than 1 instruction per cycle if you are not issuing more than 1 instruction per cycle, right? So the best you can get is 1, but practically it will be less than 1 unless you are talking about a single cycle processor. For a single cycle processor, it will be exactly 1, assuming no multi-cycle operations. But for a pipeline processor, practical IPC will be less than 1. Because in practice there will be some cycles during which no instruction completes. Right? So practically it will be less than 1. So this is not true. Okay, so statement 1 is correct and 2 is wrong. Now the same higher level language code will be compiled to a more compact machine code for a superscalar processor as compared to a VLAW processor. Is it true or false? It's true. Because for superscalar processor, the compiler has no obligation to do any kind of dependency check or to provide any kind of guarantees. Right? The hardware will take care of everything. So your code can be as compact as it could be. Whereas for VLAW, the compiler has the responsibility to deal with a lot of hazards, and the compiler has to find and bundle independent instructions. So for example, Intel Itanium, you have a bundle of 3 instructions. What if it can't find a third instruction that is independent, that can be scheduled along with the other 2? It will be filled up with NOPs. And the moment you have NOPs thrown into your code is not going to be compact anymore. Whereas for superscalar, the compiler doesn't have to bother at all. Right? The exact code that runs on a single cycle processor will work happily on a superscalar processor with almost certainly a much higher performance. A VLAW processor is likely to have a lower power consumption than a superscalar processor of comparable performance. Again, true. In fact, that is one of the biggest motivation for having VLAW in the first place. Right? Intel tried to have VLAW in the server market first, because server market is actually more power sensitive than a consumer market. Okay, where you probably won't care too much about that $10 increase in your electricity bill, but for a data center, that does make a difference, because there is a lot of servers that will have their power added up. And why will it consume less power? Because a lot of stuff is already done at compile time by the compiler, so you don't have to do a lot of runtime analysis, like whether these instructions can go together, etc., etc. So that circuitry that is required to do all these comparisons and dependency check need not be there. That already reduces your power consumption as well as possibly hardware cost. You also may not require much forwarding, etc., because the compiler will ensure that the instructions are sufficiently spaced, which eliminates the need for forwarding. So all these can reduce the power consumption. Now, since the code below does not cause a row hazard, a superscalar 5-stage pipeline RAM processor can execute the LDR instruction ahead of the STR instruction. So here you can see it does not have a row hazard. A row hazard happens only when something that is some register that is written by an instruction is read by a following instruction, which is not the case here. It's actually the other way around. Right? So is it possible for LDR to get ahead of STR? No, because of two reasons. The first reason is there is an anti-dependency. So if LDR gets ahead of STR and writes to R2, and if STR is reading that R2 that was modified by LDR, you are getting it wrong. Because according to the program order or logic, this R2 is not the value of R2 written by LDR. This is some R2 that was written by some earlier instruction, not by LDR. So if you push LDR ahead, you will end up forcing the store instruction to use a wrong value of R2. So how do you prevent this? Through register renaming, right? This is a storage conflict. This is an anti-dependency. Anti-dependency and output dependencies are what we call storage conflicts. They manifest because we are attempting to reuse R2 after this line. So the purpose of R2 here was to send some information to the memory. Once that information is sent to the memory, you don't need the value in R2 anymore. And now I am just using R2 to store a fresh value. This is how we typically do assembly language programming, right? Once we realize that the value in a register is no longer required, you will use the same register to store something else, right? So that's why it manifests. This is a storage conflict, and it can be resolved through register renaming. So you can rename these two in such a way that they use separate physical registers. So the register that STR uses as a source is no longer the register that LDR writes to. They are two separate physical registers. So any coupling between them is now decoupled, and it's okay, and it's really fine to be decoupled because this R2 and this R2 refer to totally different things. They don't refer to the same thing. They refer to the same thing only when there is a true data dependency. Otherwise, they don't refer to the same value. So you can use separate physical registers, rename, and now LDR can potentially get ahead of STR. But there is another problem. What is that problem? What if R3 plus 4 happens to be R4 plus 4? This is not known in advance. This is something that might be apparent only when these two instructions are actually executed. They have to reach the execute stage where address is computed. Only then will you know whether the address they refer to is the same or not. If the address referred to is the same, then LDR is actually supposed to read from the location that was written by STR. So there is actually a dependency through the memory location. It's a sort of a true dependency through the memory location. And if there is a true dependency of any sort, you cannot push the dependent instruction ahead of the source instruction. So this is the one which supplies the operand. This is the one which takes that operand, right? And if they are the same, then you cannot really push LDR ahead of STR. So if you do push LDR ahead of STR, you have to do it based on the assumption that they don't refer to the same location. That is called load speculation. Okay, this is done by a superscalar processor at runtime. It can make this assumption, and that will allow load to be scheduled earlier. And load being scheduled earlier is beneficial because if a load causes a cache miss, it can cause a huge penalty. So by pushing it ahead, you can hide some of those possible cache miss penalties. But later on, you have the obligation to check whether your prediction or your speculation is correct. And if your speculation is wrong, any result that was created based on that speculative execution has to be discarded. And those results should only be buffered, they should never be committed until the speculation is cleared. But I mentioned in the last class, this kind of stuff can cause security issues. Like for example, if this load causes a cache miss, okay, the cache miss, the fact that it causes a cache miss is something which leaks information, called side channel information. Side channel attack is an attack whereby other information, like for example, related to power or related to usage of certain hardware, etc., can leak information from one program to another program. That is from the attack program to the attacker program. So that does cause all these kind of issues, and that's why load speculation is quite risky to do, and many modern processors actually don't. Okay, so that completes what we have here. The rest of those were discussed in the previous class, right? Okay, so now the time is good. We have 5 minutes before we can start the quiz. And once the quiz is done, I will go through the quiz solutions, and that's about it for our lectures. Yeah, there is no lecture continuation after the quiz. There is nothing to write. This is entirely true. Because the register relay helps only with storage conflicts, and storage conflicts arise only when you attempt to rearrange instructions. For an in-order processor, the only two hazards you have are data hazards, the normal data hazards which are true data dependencies, and control hazards. And neither of them can be helped by register relay. A multiple issue processor supporting simultaneous multi-threading has more structural data and control hazards. Obviously, you will have more data hazards and control hazards simply because there are more instructions that are at various stages of execution at any given time, right? As compared to a single issue processor. And structural hazards are also likely to be higher because more instructions are likely to compete for the same hardware resources. And that is especially severe in a simultaneous multi-threaded processor where there are instructions from various threads that are competing for the same hardware resources at the same time. Yeah? Then statement A, the nodes in a computer cluster typically do not share memory, which is true. Because a computer cluster is loosely coupled, and loosely coupled by definition is the lack of a shared memory. How about computer grids? Totally not, because computer grids are even more loosely coupled than a computer cluster. They are extremely loosely coupled. You could have it geographically very widely dispersed. They absolutely do not share any memory. So both clusters and grids communicate with each other using message passing, using messages, not by sharing memory. Yeah? So this is not true. Okay, so that will make it A being true and B being false. Then the correspondence between pseudo instructions and machine instructions is visible to the programmer. Yes. The correspondence between machine instructions and micro operations is not visible to the programmer. Yes. Pseudo instructions are translated to real instructions, and you can actually see it in the machine code. Okay, so it is visible to the programmer. Whereas micro operations are truly an internal detail of the processor. It's not something the programmer can see. It's not something the hardware manufacturers want programmers to see. It's purely an internal implementation detail. So both are true.
Oh yeah. So the first question I asked.
The accuracy of a branch prediction based on a one-bit branch history table is.
I don't say you buy it.
Yeah, you don't have enough information to get. All the examples in the lecture notes are based on a loop that is executed 10 times. And all the percentages are specific to a loop that is executed 10 times.
You don't mind buying it.
You cannot categorically state that it's always 90% or 90% or whatever. It depends on whether it is a loop or not. It also depends on what the instruction does. Like for example, if it's to implement an if condition, unless you really run and see, you cannot really tell any percentage because it's very data dependent. Even for loops, unless you know the loop count, you cannot tell. Yeah. Which of the following is a potential advantage of PLIW? I think it's easy and give away scalability. Because potentially more scalable, you simply need to add more instructions into the bundle and more functional units. A single cycle processor has a CPI of 1, whereas a 4-issue superscalar processor has an ideal CPI of 0.25. IPCs for CPI is 0.25. The average number of cycles required per instruction is 1/4. Okay, because in an ideal scenario, 4 instructions complete every cycle. Then perform register renaming to eliminate storage conflicts. This is A. This is A. How about here? A. This one? A, because it's a true data dependency. And here R2,
I changed AD.
B, because now it's a fresh use of R2. And here R3, A, R4, A.